So let's look at the first question. I think you're already studying about the MOF and coordination polymers, and you did. Professor has taken a couple of lectures regarding that. So this question belongs to that. So here is a description of packing from a paper in the structure of a zinc BPY structure. So the zinc BPY structure I have drawn here, and the distorted octahedral of the zinc center is bonded to two nitrate molecules, forming a plane, and nitrogen atoms of the BPY linker are bonded to axial positions and resulting in a one-dimensional structure. So you can see here the zinc structure, which is bonded to the two pyridine linkers, as well as the two nitrate linkers and two aqua molecules. Okay, and that's forming a distorted octahedral structure over the zinc, and it's forming a one-dimensional structure first. Then it has like a pi interaction. I couldn't able to draw it, but if you look at it, if you can imagine a bit, you have a pi like these pyridine linkers are there. They glue can form a pi interaction. So that's what the second point speaks about. This is a further assembled by a pi interactions between the pyridine links from the adjacent strands to form a two-dimensional aggregate. So if you look into the one strand and another strand, you have pi stack, and therefore keep continuously forming the aggregate. Okay, and if you also consider the existence of OH and N OH and N strong hydrogen bonds between the nitrate and aqua molecules between the neighboring strands, and the third dimension there is a three-dimensional structure. So if you look at it, there's a pi stacking going on in the one above the plane, above the body can look into it, and second one is going already here, so it's already two-dimensional. Now if you are considering the hydrogen bonds, okay, that's going to be third dimension. So is it if you want to look into coordination polymer structures or coordination polymer definitions, whatever you have studied it, is it a one-dimensional polymer or a two-dimensional polymer or a three-dimensional polymer? And what is the right answer? And can you justify that?
One dimension.
One dimensional. If you heat and remove the water molecule, good one.
Good one in advance.
Good one.
Thinking way ahead.
I think you have studied today also. So examples, yeah. But if it is not removed water, because we do have a pi stacking and non-covalent interactions, hydrogen bond. Can you consider the coordination polymer dimensionality?
Sorry, sir.
So we do have a non-covalent interaction such as pi interactions and hydrogen bond. Whenever you're looking at the dimensionality of the,
We don't consider that.
we don't consider that. Okay. How about others? Do we consider, especially coordination polymer? Yes, the answer is right. We don't consider. We do have interactions, but we only looking for covalent and coordination bonds. Whenever you look at it, we do have a lot of non-covalent interactions, but we don't consider them. Okay. We can go to the second question. I think, sir. Yeah, question. I think you would need to take this.
Okay. Can you go to the next? Yeah. Just okay. All right. So let me read out the question. Can you group the same type of supramolecular isomers to the following list? Explain the reason for your classification. These are the structures. These structures are constructed from M as nodes, L as linear spacers. Okay, I'm given the three-letter word to describe the structure. How would you approach? Who will tell me the answer? What do you do first? Assume that in all this, we have drawn those things, right? Assume that the node, that's a metal, not cluster. Yeah, whatever the bond there's a linear spacer. You can put in anything, but it's easy to consider as. So, how would you approach this? You need to, I have a bunch of things. You need to group them in different. What is Now, how would you approach? See, what is the supramolecular isomer? What's the definition? They should have the same this, but not that. They should have the same. Isomer means they should have exactly same molecular formula. Okay, in this case, I consider you as M and L. Means you need to classify, find out M and L in GIAN. What is the metal to ligand ratio in GIAN? Tetrahedral, right? It is shared. So each bond is shared, each spacer is shared by two different metals in tetrahedral. So what is the ratio? M? This is the way it is shared, right? Then it goes. Okay, that's extended. So if you consider this, it's got how many linear spaces? 4. So what is the contribution to each? Same thing here, something here. So totally 10 and 2. Exactly. So now let's consider FES. You remember FES structure? I mean, you can refer. I mean, it's not that difficult to. This is again here, same. Okay, this is again.
I think they come.
Thing like this, it goes on. Right? Now you remember, this is the 4-membered, 8-membered, 4-membered, 8-membered. So if you consider this as M, this is M, all this, you can consider any one. Okay, this is contribute, what is the ratio here? Half. So for APS. And then yep. All right, now for HCB, honeycomb. You don't even have to draw. It's a hexagon, right? The hexagon.
Between 1 and then 1.5.
Exactly. So that is hexagon, HCB. What is the fourth one? HXL. You remember? Is made up of what? HXL. Well, you can see, or if you don't remember, all triangles. Right? It's all made up of triangles. Why I'm drawing hexagon? Okay, so you can draw, you can extend it. So consider this as your M. 1, 2, 3, 4, 5, 6. So for HXL, what is the next one? Oh. Oh, no, I should have. KLA is not. Okay, I didn't. I should have. I thought I deleted it. KGM and all. Okay, let's not consider this because we haven't So I thought I deleted and, but I forgot. Okay, let's forget about KLA and KGM. I haven't taught you, okay? But PTS and SQL, PCU,
PTS.
then PTS, PTT. Okay, now MOG.
No, last one is SQLs.
Oh, SQL. Oh, yes, SQL. Okay, MOG.
Remember the structure actually of the mog.
What is that?
Remember the structure of mog and.
Yeah, it's all from mixture of what? MOG structure. Take a look. Stobolite, it should have mixture of tetrahedral and square planar. Square planar and tetrahedral in the ratio of, is it? Yeah, take a look. Take a look and let me know. What is it? Binodal. But what is that? What is the how many bonds are there on each? Exactly. So it should be. Yeah. So how about PCU? PCU is sodium chloride. So yeah, no. That means ML 8. PDS. Again, all square planar. That means M L 2. SQL.
And this gives it as both. Yes, as.
That's okay.
Yeah, 4 means 4 bonds with the node, fine.
Okay. How about the last one? SQL. SQL is square planar.
Well,
Yeah, exactly.
ML2 as one group.
Now you group it.
ML2
Maybe you can include this one
first
and
one.
this and this and this. You have to add amount to this.
This.
Okay, that's about it. Right? So this is to understand the definition and then how to find. See, I think I gave you an exercise how to find the molecular metal to ligand ratio in various things. This is the way you do that. Okay, so totally you can find out what is the molecular formula and then you can decide whether it is supramolecular isomer. Any question? Okay, good. So I included a few more which I haven't discussed anyways. That's why I thought I deleted as usual. I just included. Anyway, you can go and find out about KLA and KGM. A little bit more, complicated, but you can understand if you follow the lecture.
Even the next one also.
Next one also. Okay. All right. Now, cadmium. You mentioned cadmium cyanide, N-butyl ether as hexagonal diamond dot. I think I tried to discuss in the class. And also when we discuss MOG structure, I had given this formula. This again, it's the same cadmium cyanide that has got the MOG structure. So now, how come the cadmium cyanide formula is here? It's exactly the same. It's a N-butyl, this is tertiary butyl alcohol is there. How can you have different structure? Completely different. It's not diamond dot or hexagonal diamond or cristobalite or lanzolite. This is Mog topology. Can you explain? What's the difference between the dia and the mog? No, for dia, it's made up of tetrahedral, right?
They are all tetrahedral.
They're all tetrahedral. Okay. Whereas in this case, mog,
Tetrahedral as well as square planes.
square plane.
Yes.
Tetrahedral, you can understand. For cadmium, can have tetrahedral. Square planar. Can it have square planar? Do you remember? If you have, there is the geometry, the coordination geometry doesn't have any bearing on the what is the topological thing. That be the case. You remember cadmium nitrate bipyridyl structure I was trying to show you, and also one more with dicyanide. So there is 4x4 can be the node is square planar node, but it can have tetrahedral coordination geometry of the metal. Same thing with cadmium. I try to discuss cadmium with square planar bipyridyl with 2 nitrate on it. Actually, the coordination number is more than 4. It's not square plane. It can be octahedral. You can also put chlorine. So what does it mean? Does it ring a bell? So you have to somehow think of this one to have, yes, tetrahedral, node coordination geometry. Of course, cadmium can have. The other cadmium, because you have 2 different types, right? The other one should be square plane. Let's try to write square plane. Let's see whether you can get anything out of it. Okay, now I'm putting something here. Can this be called square plane still, topology wise? I'm not talking about coordination geometry. Coordination geometry is octahedral. So you go back here, the formula. So you need 2 types of cadmium. One type of cadmium it's got tetrahedral, CN, CN, CN. The other one, the cadmium, is CN, CN, CN. It is like this. How do you satisfy? What is the ratio of octahedral to tetrahedral according to Mog? 1:1, 1:2, tetrahedral to square plane. 1:2, right? That means this one should be 1. Cadmium, it's 6. Okay. And then the other one is 2. Cadmium, this is 4 coordinate. Now, can you incorporate here? How about water? 2O. I mean, the way it is written, okay, it's confusing. So it's exactly bonded. So now, can you write the formula? So I'm saying that it has got now square planar node, tetrahedral node, and also I have given the ratio. Now you can write the formula based on that. So that's what is happening in the structure. 1:2 of square plane. So that if you have 1:2, there should be 3 cadmium. Right? 3 cadmium. So the formula should be 3. So once you triple it, that should be 6. And then you got only 1. So it has to be 4 times. So tertiary butanol is not bonded. And you can see because you already multiplied by 3. So this is the actual formula. And actually, if you want to write, so one cadmium should have this octahedral geometry. The other one should have tetrahedral geometry. So that's the way the structure looks like. Okay. I mean, don't fool by, cadmium sign. Okay. So it has to be, I mean, it so happens it belongs to Mog topology. Do you follow? Right? Okay, now, is the formula consistent with this one? The formula consistent with that one. Okay. You need to divide by 3, and then you'll find out. That's it. It means this is right. Any question? Okay.
So let's go to the next picture. Here's going to be the question number 4. So predict the hydrogen bond connectivity in the crystal structure of 4-hydroxybenzoic acid. So you have studied the synthons and you have studied different type of hydrogen bonds and try to draw the what is the hydrogen bond connectivity in the solid state or at least in the 2D place. Can you just draw something? Yeah. So if you want me to draw the structure first, please. So there basically have 2 type of synthons you come in. Any other? There is one very good synthon like get at carboxylic acid will form some specific synthon.
Yes, sir. So we are studying the hydroxy.
Okay, no, that is fine. If you look at the 2 carboxylic acid, can they form any synthon out of it?
Which is the most likely, the strongest one. That's what you have to write first.
So these other ones are the weak. No, not in intermolecule. Intermolecule cannot.
It's a packing. It's a crystal packing you have to draw.
Yeah, that's the one. Like if you look at the 2 basic acids, what's the first one you should look? That's a strong structure. And how would OH? OH over? Then how the OH gonna be interacting? So whatever you study in more and more, don't lose the fundamentals. This is gonna be like your benzoic acid, like carboxylic acid are one of the strongest in this one. Then OH any idea?
Phenol also we discussed in the class. Yeah, how phenol can interact There are a lot of examples also we had given.
Phenols, hydrogen. In the six, it will be surrounded by six phenols.
Okay, so you're always thinking about the carboxylic acid. OH itself,
There is
we have phenol.
one that
Consider.
we discussed. And
Carboxylic.
shown in that class also.
So that's gonna think of that. Yes, it is also possible. It's not,
So
we are not.
usually phenol, you have got one donor, one acceptor. That's it. Okay.
Another famous result, and it's the strongest. And you see the 8 number of atoms in the same. And if you look into the voltage, like consider this is the strongest. So carboxylic acid doesn't have any other role in this anymore, right? Most of the time. Yes. Yes, I could see like most of you are trying to draw this one actually. It is going to be less.
Right there. So this online people can also see.
Right there only.
So this
I want to continue this. That's where I was just stuck. No problem.
here. Here. Brian.
Okay. Oh.
You're trying this one. I could see that, but it's like if you look at it, you have a strength is significantly lower. Reason is maybe this is strong, but this may not be that strong as this one over here. Okay. I know like even some of you could write like only like OH and they have somehow like I don't know. Yes, they have kept it this way. So they try to put it this way. So
Carbonic.
You can argue that may be a kinetic product.
both are possible.
You have to go for highly thermodynamically stable bond.
That's hypothetical.
Yeah,
It can be there, but the way how you make it gonna be the tricky part there.
I mean, make it simple, okay? I mean, it's a straightforward question. It's not PhD. You have to make it.
So what if we only could create the interaction between carbonyl and H? Only one interaction, not the other one.
Why not?
Then it will form a linear type.
That's what a couple of people wrote is.
Yes.
If you have carbonyl, yes.
Yes.
If you have a carbonyl, it's not carbonyl, it's a carboxylic acid. You also have OH. It's a carbonyl, yes, it will form.
OH will, no doubt that it will weaken that interaction at the end.
Just for argument's sake, we can argue too.
So that's what your some of you wrote it actually.
It's a straightforward one. Acid dimer is very well known. We discussed about it. That's a simple, you can expect.
Yes.
So phenol,
Continuously.
we discussed how it's forming, one donor, one acceptor.
Yes.
That's about it.
It's both.
And take one more, the dimer, put it on the other side and, have OH, phenolic interaction forming.
Yes.
Yeah, that's it. It's very simple. You don't have to, put it down and then go, yeah. It goes zigzag OH, you can just write
This one.
this. Yeah. From the neighboring dimer, it is forming, It goes back, you don't have to. Yeah, the dimer is forming that way. And then the one will.
Is this interaction, new interaction which we have made between the two already existing dimers, is it enough strong to have?
Just let me draw it, then you get idea.
Then
So it's going down on this side. OH. On the other side also it's the same thing. Make it simple. And then you get a sheet.
yes.
And then you can put pi to, have a second layer. That's it.
3D.
Gone.
Then you literally get another molecule. It's continuous flamer and you also have everything arranged.
It could be the example of homosynthesis.
Yeah.
Yeah,
absolutely.
Example of homosynthesis.
Yeah.
example, not example.
Yes. But
Both are one face.
Same and obviously it's homosynthesis. Then let's go to the next question actually, which is going to be the follow-up question actually, as Sahil was pointing it out. Provide different examples for performance heterosis. So you have studied something pyridine, right? Pyridine and carboxylic acid, one more. Is it homo or hetero? Okay. Anything more? Styrene. Styrene has any hydrogen bond? in it?
Peptide bond.
In peptide, there are many.
Yes, sir.
Come on, draw.
Peptide now, and would be huge.
Peptide gonna be, yes, they are mostly like homo and mostly hetero also there. Yes, but there are many. Anything more like one is a carboxylic acid, which we already drew it. Second one going to be pyridine, right?
Okay, yes. Then homo with pyridine.
How do you get the pyridine?
Yes, here and.
Then that becomes heterosynthesis, not homo. Yeah.
Okay, both the pyridine.
Where is the hydrogen coming in?
No, I mean, I know you guys raised this issue, but there's nothing known in the literature that pyridine forms something like what you said.
Carboxylic.
Yeah, two pyridines, I mean, we discussed in the class. Yeah, but I don't think it's known. It's a good thing, you should take it up as a challenge and try to make one and show that it is possible, or computationally you show.
Yes.
Yeah. Where is the other hydrogen coming there?
Yes. Ortho to the nitrogen.
Yeah, CH.
Ortho to the nitrogen. Yes,
This is one.
same we get to the thiol and acid.
Is it good acceptor?
Not that good. But you can have your sequence. Is it a good acceptor you said, na?
It's a good
I-
acceptor.
This line, I want to apply this line on the structure that when you bind it up to different dimers at
Mhm.
that place. So oxygen is bonded to hydrogen. Yes, this.
Yes, if you have hydroxide,
Yes,
it's a very strong donor as well as acceptor.
and it has already formed one interaction.
Yes.
Is what thing is deriving it to form the another interaction with another moiety?
So this is already forming one.
Yes.
I mean, and it's a
Why it is
donating
forming
it.
that upper one there?
So you look into it actually. It's gonna be delta positive. Delta negative. This delta is not standing behind. So obviously this will try to interact with again delta positive, right? Don't miss that. Again here, like what's happening is charge prolongation.
Mhm.
In fact, if you look into bottom marking, it forms two.
Yes.
So it still has enough ability to take. You have two lone pairs and it has enough ability to look up.
You remember I had given the whole slide full of synthons.
Yes.
All are homosynthons.
Yes.
All are homosynthons. One slide.
Can we took
Pyrrole.
in heterosynthesis, can we took the example of phenol formaldehyde acid?
you have to come and write down.
Okay.
I mean,
Yeah, it's okay, come on.
Come on, write it down.
No, phenol and
Sure.
And you can also look into like another molecule such as like urea.
that can be used.
Urea is a very good molecule for the synthon actually.
Yeah,
It's
come
almost
and write
like
it down.
ketino.
Actually,
got
I
the
have
homework.
given the answers in the one of the slides, full of those
Careful,
those
careful,
results. If you take a look at it very carefully. It's about at least 6 or 7 or even more than that. Under different heading.
And if you remember like adenine relative nucleic acids we have studied, right? All are again other synthons. ATGC.
To form one.
Let's try it, draw it. If you want to put it this way, this. But it is, that's the hydrogen, carbon, that's the I'm talking about. Of course, it is possible, we don't deny that, because even CH is known to show good amount of hydrogen bonding.
Then it can be also, CH is known to show,
It shows in exception several cases, but not completely every
you
time.
can use mesitylene or super mesitylene groups also.
Okay, mesitylene, which is like a
CH is
1, 3, 5.
Yeah.
Substitute.
Mesitylase.
Yes.
Mesitylase is 135.
Yes.
That's it. I mean, what do you expect? You can't include Van der Waals. Interaction, that's not form of synthon.
Mesitylene is very
Sir,
difficult.
will it form orthoxylene?
Okay, I mean,
Heterosynthon.
I don't think that is possible.
Why, sir?
It doesn't form a, kind of a dimer.
The
It
salicylic
tends to form, or when you have OH, tends to form some kind of cyclic kind of thing. I don't know, because I mean, we have to mention that provide known examples, and then provide your imaginary examples. I mean, I should have, put it, so I expect you to go through some literature, not come and, try to make, yeah. I mean, well, it is possible, I'm not saying that it is possible, but it's more, on the paper, yeah, you can argue, but, that's fine. But you have to, I mean, I thought you guys will immediately go and look for those things.
Lights.
It is known already, which has been proved, I mean, so that's what I was expecting. But I'd given a whole bunch of things and if I tell you where it is, then you will know. I mean,
Is that actually there was one slide that always
no, homosynthon, for heterosynthon, I had given under different things. Anyway.
Because if you look into the Desraja,
Yeah, please.
if you look into Desraja, I'm pretty sure he would have happy like with the CH.
Yeah.
heterosynthon at the place of pyridine, we can use pyrrole.
Yeah, of course.
And urea also you can look into it, by the way.
Yeah.
Urea as well as the
There are so many synthons that are known. But yeah, sure, why not? But if you take it from the literature, it's we are confident. Do you have your notes? Look under isographic, that I described towards the end of this, the chapter 2. Isographic, groups.
For example, if you want to take it up to like a nitro. Is this homo hetero? Hetero, right?
Yeah. Even iodo, nitro. Yeah. Nitro, put the iodine in the middle, yeah. You know? Good. Yeah. I think we have discussed quite a lot. Actually, most of the halogen bonds.
Yes, they are like.
Yeah, where you have S, I, SCl, SBr kind of thing. Yeah.
Okay, then I think we have several of them, and you can also dig it out of the notes actually. Then, yeah, last question is like benzoquinone is yellow. How many of you remember the structure of know the structure of benzoquinone? Okay, benzene. It's a ketone. Give me a minute.
Right.
Then, okay. Benzoquinone is the yellow. What is hydroquinone? Which. And this is a yellow in color, and this is a colorless. And if you contract hydroquinone crystals into the in contrast, actually it's a contrast. In contrast, the hydroquinone crystals are blue, black, and nature.
Yeah, spelling.
Yeah. In contrast, if you look at the hydroquinone, twin hadron structures, which is a combination of these two.
Yes, queen hydro.
Twin hadron. If you have a combination of these two, the color is blue, blue black. Actually, it looks like very black in color. It's supposed to, it's yellow in color, and it's a colorless. So if you know the combination of colors, if you combine two colors, you are supposed to get something else. So it's a white and a yellow. If you combine it, what is supposed to be color? Pale yellow, light yellow. But rather, what is happening here? Any reason? Any explanation? What's going on there? Any idea actually?
यहाँ ऐसे ही बना लेंगे तो पैकिंग से कुछ होगा
It will be forming well and good. They have interactions obviously. So this will oxygen will when they are forming together, oxygen will form a hydrogen bonding with the OH and they forms a very nice structures. But what makes the color change significantly? You are absolutely right there.
That hydrogen can be conjugated. And one side it will be oxygen. And
क्या बोलते हैं प्रोटॉन चेन एक्सचेंज
from another compound. So that the electronic is not the rings that electronic configuration will be destroyed.
Okay. Then
That is an impact of exchange.
okay. If you want to put it in energy level diagrams, can you help me to explain that? Not the Teflons. You look into like the homo-lumo gaps. It's like a homo-lumo or like a conduction and valence bands. If you want to look into it, how does it happen? First of all, we have studied the coordination chemistry, right? What is the color? Usually, what happens in whenever like if you get like a electron spectroscopy, what kind of transition way to way? Not always you have metal, okay? There doesn't have any metal, so you should not. There is no emergency LLCT here. There is no LMCT here.
You are talking in coordination, that's fine.
But like if I have been explaining, every color is because of some kind of things. So excitation. From where to where it happens.
When bandgap is less larger, then we get the stronger color, red or etc. Like
Band gap is higher.
Yes.
What happens? Color is stronger.
yes, reddish.
Band gap higher on the cap. If its band gap is higher, then what is the color supposed to be?
Towards the reddish color.
Is it?
No, sir.
Whenever band gap increases, the energy should be increasing. Whether red has a higher energy or violet has a higher energy.
Sir, he is saying the emission like color he's saying.
Huh.
Complementary
No, no, no,
color.
no.
Yeah, that also.
You're looking at a complementary, but they're different here. We are looking at like one more different perspective. Don't go. If you okay, I think your coordination chemistry complete gone out of your head. I could see that. Or at least like whatever the MOT I have taught, a lot of things gone out of your head. It seems I had to take exam then. Then you'll read it again.
इसके लिए energy ज्यादा
Whenever there's a color change,
ज्यादा लगेगी.
what is it due to? Usually the color.
तो उसका complementary
In general.
करेगा.
Color change is due to what is disturbed, what is perturbed.
नहीं तो energy ज्यादा मतलब
What is perturbed?
बोल रहा हूँ. ये
Yes, but how do you make sense of
You
the
got
color?
it, that's it.
Yes.
Now you can find the answer.
अगर वो सबसे
It's like always your
Right.
electron go from the lower energy to the higher energy, right?
वो
What's the lower one called and higher one is called?
तो यहाँ पे absorb ना higher energy का करेगा.
Homologue, yes, right?
कलर दिखना तो हमें lower wavelength.
So this has some kind of like homologue. Okay. And it's and another one is having a higher actually. Yellow color means it's a complementary color. What is it? Orange. So this is around roughly in the range of 600 or 500 range, right? So, and the next one is going to be the colorless. So what is the absorption most likely?
Green.
Colorless.
Colorless. Colorless means all light. All light. No.
Either it absorbs it.
All
If it is absorbs everything, it should be black.
Yes, all will be reflected.
It is colorless. So what is its absorption?
UV light.
Light will reflect all the lights.
Somebody was saying the answer actually.
UV light.
UV light actually. It absorbs only UV. It doesn't absorb any part of the visible. Any part. If you remember it, if it absorbs everything, it should be black in color because you cannot see that.
Only black, only cannot.
But if you observe in UV, you can't see it. Then there is no complementary. Obviously, and your right side is what is falling on is coming out of it. Okay, it's white. So it's gonna be and UV means it's kind of gonna have a significant energy,
Yes.
right? And now you see here there is a possibility, or maybe you can also put it like a little bit possibility over here, something very black. Now you have combined both the molecules. Now there are several transitions can take place. This can take place, right? Now you are bringing another reference. This can take place, right? And if you give enough energy, of course, nothing more. Actually, these are basic two transitions. So what is happening? One molecule. This is a molecule from the like benzoquinone, hydroquinone to the benzoquinone transition step. What is it called? LLCT. If you look into it,
Yes.
ligand to ligand, but there is no ligand concept here anymore. There's no metal here. So everything is happening with the like charge transfer between the two molecules. There is no metal there.
Okay.
It's a charge transfer is happening. So you have two molecules. The electron is moving from one of the orbital of the one metal molecule to the another molecule. And this energy is good enough, and most of the like what is a complement?
Orange.
Blue.
Yes, blue.
Orange.
Orange. Blue, orange, yes. Yes.
Yellow is also orange, is it?
Complementary to blue is violet. Violet ka yellow.
This one gonna be violet, right? Or complementary?
Violet ka yellow. So violet should be absorbed.
Violet is absorbed here, and now it is like the energy gap. Compared to the violet, whatever is like orange, supposed to be lower in energy, which makes sense. Your energy is getting lower, okay, and it is absorbed orange. And the transition is highly feasible because if you remember, like most of the times whenever we study it, the laboratory rules and all these things happens within the molecule. And if you have second molecule comes up, there is a significant mixture of orbitals. Laboratory rules gonna be a little bit relaxed, and absorption gonna be significantly higher in nature. Then the charge transfer is significantly stronger, and that makes it. So blue, of course, the transition is blue, but black color because it absorbs a significant part of it. So literally, most of the photons, whatever you go there, they got absorbed. that makes the color to be blue black. Maybe if you can add up.
Yeah. I mean, see, when you have two different compounds, okay, you want to find the answer. The answer is within, it is there already. You need to consider the molecule. Don't think of anything else. Look at the carbonyl one. This is completely, the electron is depleted. With the other one has got a lot of electrons. Yeah, immediately you see that there should be a charge transfer. Okay, I mean, the answer should be there within, the given the molecule, two molecules. Where else it can go? How it can orient itself for the color. Again, whenever there's a change in color, it's the electronic. When there is an electronic, there should be a transfer of electrons, and then only you can excite them. So immediately you should think from that point of view. Of course, higher hydrogen bonding and everything will strengthen, but that will reflect only in IR, not in electron, the color, right? Only around 3,000 Dave numbers, it will be shifted. Where you have OH, frequencies. Yeah, that's it. Yeah.